So, welcome back student to the next class of Introduction to Nonlinear Optics and its application course. So, in the previous class we learned about the sum and different frequency generation, and also we know how the second harmonics are generated. Today is the lecture number 16 and let us see what we have in today's lecture. So, today we have two very important concepts. One is nonlinear Maxwell's equation, and we will after having the knowledge of nonlinear Maxwell's equation, we going to learn the theory of second harmonic generation. So far roughly we understand how the second harmonics are generated. So, when we launch an electric field, because of the frequency mixing, different frequency components are generated, and if we launch one electric field with frequency omega, then we find that we can generate frequency 2 omega, which is called the second harmonic generation. But the detailed theory is still missing, because we do not know exactly what is happening inside the medium and how the second harmonics are evolving, how the second harmonic fields are evolving are still quite hazy. So, in order to understand the detailing of the second harmonic generation or the basic physics or what is going on inside the material, it is important to know what is the meaning of nonlinear Maxwell's equation. Well, the Maxwell's equation is the governing equation, the main governing equation of the electric field. So, when the electric field is inside the medium, what happened that it will interact with the medium, and if the interaction is nonlinear in nature, inside the Maxwell's equation we have some kind of nonlinear components, and this nonlinear components is nothing but the nonlinear polarization that we have been learning for last few classes. So, let us try to find out how to calculate this nonlinear Maxwell's equation or how to derive this nonlinear Maxwell's equation. Okay, the derivation is quite straightforward, and it is something like the way we generate Maxwell's wave equations, exactly we will generate in the similar way the nonlinear Maxwell's equation or nonlinear Maxwell's wave equation. So, let us start with our fundamental expressions, that is d, which is epsilon 0 plus p, displacement vector is epsilon 0 e plus p. Now, it is not necessary that d and e should be in the same direction, because of this polarization can be a function of electric field. But if I launch the electric field, that not ensure that the polarization will be in the same direction. If the medium, especially if the medium is anisotropic in nature, then there is if I launch an electric field one direction, then the polarization will be another direction. So, we will come to this point later, but here more importantly we need to introduce the nonlinear polarization. So, now the polarization can be divided into two parts. One is the linear one and another linear part, and another is the nonlinear part. The linear part is introduced in this way, and it is proportional to the electric field as usual, and if that is the case, then the d can be represented at epsilon 0 e plus epsilon 0 chi 1 e, which is the p linear term, and then p nonlinear term. We just left the p nonlinear term as p nl vector. Okay. After having the value of d, now it is time to write in a compact way, and if I do, then it should be epsilon 0 1 plus chi and e, and we know that epsilon 0 1 plus chi is nothing but epsilon 0, and p nonlinear will be there. So, if I look from this equation to this equation, what essentially is changing? D was epsilon 0 e plus p, this p is the p total. Now, I combine this p linear term here, and in this p linear term we have the information of the refractive index, that is the material information, that is we basically inserting that material information into the system through refractive index. and that is why this epsilon 0 become epsilon, and since a nonlinear part is associated with this. So, this nonlinear part will be left alone and it will be simply that. So, from here to here we make certain modification, and the modification is essentially we just separate out the nonlinear polarization term and the rest part is same. If nonlinear polarization is 0, then d equal to epsilon 0 E is the standard form that we usually find when we calculate the Maxwell's equations and the corresponding derivations. Okay. Okay. After having the knowledge of D with nonlinear polarization as shown here in this is the expression that we figure out. Now, we start deriving the Maxwell's wave equation with this condition, So, now again we will going to use two curl equation. So, curl of E is minus del B del T, curl of H is minus del D del T. So, now if I take curl both the side from this equation, so curl of B will be this, and if I take curl of H both the cases, so I use curl of if I from this first equation, if I do curl of B, it will curl of B, and this curl of B I use this one, and then it will be curl of H with mu 0, because B is mu 0 H, and then curl of H I will going to use this term. So, it will be the second derivative with respect to second order derivative with respect to time and D. So, this curl of E can be represented in a standard form. We know it is a grad of it is a grad of divergence of E minus of grad square E, and then the right hand side is minus epsilon 0 d2 d dt square. This term is now represented into two parts, one is this and another is this, because my D is epsilon 0 E plus P nonlinear. So, when I write double derivative of D, essentially in the right hand side I need to write this is not this is epsilon. Okay. So, let me clear it and do it once again. So, I am making the double derivative of D. D is this, so it will right hand side it is simply the double derivative of E plus the double derivative of P and L. So, I am making, if I use this, it will be simply this quantity. So, now grad dot E is 0. So, this term will cancel out. So, eventually we have this is equal to the right hand side. So, this is the equation that is given inside the border we have. One very important aspect we find in this equation, that in normally this term is not there. When we consider if everything is linear or the polarization is a linear polarization, we have this is equal to 0, and then we have some kind of solution, because this is a plane wave, the plane wave solution is there. So, we have already done in our basic linear optics course. So, now instead of having 0 term, what we have is a source term. This is basically a source term. This P nonlinear term basically a source term of the electric field. That means, whatever the electric field will be there inside the medium, in this differential equation we have a source term, and this source term is essentially coming with the fact that my P nonlinear is there. So, P nonlinear is basically feeding some kind of energy to generate electric field, and that is the same, this picture we have already shown with a schematic diagram, that when the dipoles are vibrating in a nonlinear fashion, it will start generating some kind of electric field, and this electric field will have a different frequency component. Exactly the similar concept we have through this equation, where we find after deriving the Maxwell's equation, considering the nonlinear polarization term, we have something like this, a source term. Okay. So, the next thing is what happened when we have the electric field into the system having frequency component. So, we have already derived the nonlinear Maxwell's wave equations. So, this is the picture. We launch an electric field and we put some kind of input and we will get output outside, but in the system, inside the system, what happened that we have two frequency components. So, if I launch electric field E of omega, if I consider only the second harmonic generation, then inside this system a second harmonic field will generate. So, output obviously we will have E omega and E of 2 omega. So, that means E of 2 omega will going to be here somewhere. So, in this figure we find that inside the material which is nonlinear in nature, we have the fundamental wave and also the second harmonic, both are present. So, for both the cases the nonlinear Maxwell's equation or the nonlinear wave equation is valid. So, for two waves we have two equations. Basically the equation is same, the electric field component E omega and electric field component 2 omega are different, but the equation is same. For electric field component E omega, what happened? The source term is P nonlinear omega, as I mentioned. So, when you launch the electric field, what happened? The dipole, if this is the dipole, it will going to vibrate at frequency omega and start generating a field of omega. So, that is why the source term is nothing but the P nonlinear, which is vibrating at the frequency omega. So, that is the source of the electric field which is generating, and the frequency of the electric field is same as the frequency at which the polarization is vibrating. Here the polarization is vibrating with the frequency omega, nonlinear polarization, and as a result we are getting some kind of electric field which is also vibrating with the frequency omega. Exactly in the similar way we can say that if this is my dipole, suppose, and it is now vibrating with the frequency 2 omega, and when it is vibrating with the 2 omega, my nonlinear polarization can be represented 2 omega. This is the way it is vibrating, and as a result it is generating an electric field with the same frequency 2 omega. So, that means the generation of 2 omega is essentially supported by the nonlinear polarization which is having a component of 2 omega. Now, if I look to this differential equation, in this differential equation in the source term, both the cases we have P nonlinear omega and P nonlinear 2 omega, two source terms are there. This source term basically responsible for generating electric field with omega, this source term is important for generating the electric field 2 omega, but the equation is same for both the cases, only the components are different. So, in the next step, that is very important to find out what should be this value and what should be this value, so that we can solve at the end of the day we can solve our Maxwell's equation. Okay. Okay, the electric field, we know very clearly what should be the electric field, because we have been using the form of this electric field for long. So, electric field with frequency component omega we just use as E1 e to the power of I k1 z minus omega 1 t plus complex conjugate of that with a half term. So, that it is real. This is the normal way to represent the electric field, and that is the frequency component of E omega. But here one thing you should remember, that this E1, this is a phase, but some additional phase should also be there. So, here we write E1 tilde, which is a real quantity, and then e to the power I k z minus omega t, that is the component related to the plane wave, and on top of that we have some additional phase which is phi 1. So, this phi 1 can be represented as e to the power I phi 1 multiplied by E 1 t, and write only the k 1 z minus omega t in a separate way. So, if I do, then I can write E 1 is E 1 tilde e to the power of I of phi 1. So, now this is complex quantity. So, this is amplitude, but normally the concept is amplitude is always real quantity, but here we absorb the phase additional phase term to make it more general and find that the amplitude is now complex in nature. So, that in the future we may have the term like E 1 star. This is the term which basically gives you the idea that E 1, which is essentially the amplitude, may have some phase associated with that. So, that is why it is a complex. So, simple thing here, how to find out what is my E omega and E 2 omega. So, in the slide we can find that E omega is nothing but E 1 e to the power of k 1 z minus omega t, E 2 e to the power k 2 minus 2 omega t, because this is 2 omega. So, that is why 2 omega frequency is there. K 1 is the propagation constant for the frequency component omega or the fundamental wave, and k 2 is the frequency component of the second harmonic. So, these E omega and E 2 omega are the electric field, and this electric field has this kind of forms. Remember that E 1 and E 2 are now complex amplitude in general. Okay. Now, we going to learn, as I mentioned, the theory of second harmonic generation. So, if I go back to the picture, as I mentioned that this picture we have already shown in our previous classes, that if I launch an electric field of E omega, the polarization will now going to vibrate. These are the polarization terms. Several times I mentioned that for this polarization term we have a frequency component P omega and P 2 omega. That is important here. I am not now I am not considering about the optical rectification term. So, this is now vibrating with the frequency omega, this is now vibrating with the frequency 2 omega. This is the source term of 2 omega electric field, and this is the source term of omega electric field. Okay. So, I know what is my electric field, right. So, electric field I have already derived. Now, the next quantity that we need to derive is P nonlinear of 2. So, I need to, so E omega I know, E 2 omega I know. Next thing is to find out P nonlinear omega, what will be the form of that, or P nonlinear of 2 omega, because in order to use the Maxwell's equation or solve Maxwell's equation, these 4 quantity is important. So, this term and this term we know what is the functional form of that, but this and this we need to figure out. So, if I want to find out the second harmonic, so P nonlinear is nothing but epsilon 0 chi 2 e square. Now, here we going to use this chi 2 as 2D. This is some historical reason people are using this D matrix rather using chi 2. So, we will also follow the same thing and going to use in different books. You find that this D, they represent the chi 2 in terms of D, but there is a relation between chi 2 and D, and that relation is chi 2 is equal to 2 multiplied by D. So, now if I use this chi 2, then my P nonlinear is 2 epsilon D and E square. Now, this E square term is containing 2 frequency component omega and 2 omega. So, omega 1 plus omega 2 and square of that. So, P nonlinear is now having E 1 e to the power of I k z minus omega t, E 2 e to the power of I k z minus omega t, and plus complex conjugate of that and square of that and half of that, because if I go back to our previous slide, let us go back to our previous slide. So, in our previous slide, here you will find that E1 and E2 is this. Once we have E1 and E2 in this form, now we need to find out what is my P nonlinear. So, P nonlinear has different frequency component, but we are using this notation and then E square. So, when we make E square, so E is now 2 of epsilon 0 d 1 by 4 and square means E omega plus E of 2 omega square, and E omega is this. So, that is why this quantity plus complex conjugate and square of that. Exactly the same thing we have done in that slide. So, I should go back to that slide where I am making the square term here. So, E1 e to the power of kz minus omega t, E2 to the power of kz minus omega 2 plus this square of that. So, P nonlinear is this. So, now what we will try to find out, what is P nonlinear omega and P nonlinear 2 omega, because when we do this entire calculation, it is for sure that I will have some component like P 0, P nonlinear 0 plus P nonlinear omega 1, sorry, P nonlinear omega, because there is no omega 1, plus P nonlinear 2 omega. These three components should be there. So, P nonlinear omega is the frequency component that is generated with a frequency omega, and P 2 omega is a frequency component of P nonlinear with frequency component 2 omega. So, now if we do that, so I can also put this is a some sort of homework. That how one can generate P nonlinear omega from this P nonlinear omega with this term, but I will going to explain that, but I want you the student to make it by your own hand, do that by your own hand. So, let me try to understand that how this P omega components, 2 omega components are there, P omega and 2 omega. So, omega components will have, so when I make a square of this term, so what will happen? We have one term which is square of this, that means 2 omega will here. One term we have a square of these things, so we have 4 omega term will be there, and complex conjugate terms are there. So, that means we have a term, say this is A plus B plus A star plus B star, complex conjugate means the star of that, multiplication of A plus B plus A star plus B star, it is something like this. So, when we do that, it is nothing but A plus B plus A star plus B star square of that. When you do the square of all these things, we will have A square term plus B square term plus A star square term plus B star square term plus 2 of AB, this couple term, plus B A star plus A star B star plus A B star, this kind of terms you will get. So, now every time you need to find out what is the frequency component of that. So, A square term has a frequency of 2 omega because this is omega. B square term will having a frequency component of 4 omega because it is square of that. A star square is a frequency component of minus of 2 omega, this is minus of 4 omega, but when the cross terms are there, then there is a possibility that we will have some terms which has a frequency component omega. And how you get the frequency component of omega? Very easily you can find that if I make a star b, which is this term, then what is the frequency component? A star has a frequency component of minus omega, b has a frequency component of 2 omega. If I add it, a star b will be the frequency component 2 omega minus omega, which is omega. Why add? This multiplication, the frequency component is inside the exponential term. So, it will be e to the power I omega, and then it should be multiplied by e to the power of 1 is e to the power minus omega and multiplied by e to the power of 2 I of omega. So, when you multiply that, this frequency component is going to add up. So, when we add up, then we will have a k term like k 2 minus k 1 and then the frequency of omega. So, you will find that we will have a frequency component of omega, but most importantly this term E 1 star and E 2. In the similar way, if I try to find out what is the frequency component of 2 omega for p nonlinear, it is nothing but the first one, that is the a squared term, because only when you make the squared term, only the first square, that means a square will give you 2 omega. So, that is why the amplitude is epsilon E 1 square here. In this case the amplitude is 2 AB. So, this 2 multiplication by a star b. So, that is why 2 multiplication of a star and b with the corresponding exponential terms. So, this exponential term basically gives you the frequency components, and when we have all the frequency components, I can determine what is my p nonlinear 2 omega and what is my p nonlinear omega. So, now we have all the information in our hands. So, we are in the position to solve the Maxwell's equation, because the p nonlinear term and the electric field term both are there. The solution of the Maxwell's equation for fundamental waves. So, how to find out how the E omega will going to evolve? If I try to find out, so I will going to use, we will going to use this equation, this mother equation, where E omega is this and p nonlinear omega is this, that we just derived in the previous page. Also for 2 omega, we will have, this is how the second harmonics is going to evolve. We will have this equation, this is a nonlinear Maxwell's equation, and p nonlinear, we just extract that p nonlinear is nothing but this, where the frequency component p nonlinear 2 omega is the frequency component, and here we find the frequency component is really 2 omega. The important thing is the amplitude here. So, we will have the expression of p nonlinear 2 omega, we have the expression of E. So, both the information is now in our hand. So, the next step is to solve the nonlinear Maxwell's equations. So, now in the next class, today we will going to we understand how the nonlinear Maxwell's equation can be useful to understand the second harmonic. So, in the second harmonic, we find that it is important to find out the source term, that is p nonlinear 2 omega and p nonlinear omega, and once we have the functional form of both p and E with different frequency component, we can use that in the Maxwell's equation, and readily we can find the evolution equation of the second harmonic wave and the fundamental waves. So, in the future classes, we just solve this nonlinear Maxwell's equation with certain approximation and try to find out how second harmonic wave will going to evolve. So, with this note, let me conclude here. Thank you very much for your attention. So, see you in the next class. Thank you.